Okay, so in this session we will continue with our discussion of this business of having two random variables at the same time. Okay. So when we have a discrete random variable x and we have another discrete random variable y, then we can talk about x and its PMF. We can talk about y and its PMF. And we can also talk about, if we're considering both of the random variables at the same time in our experiment, then we also talk about a joint PMF for both of them at the same time. Okay? Now, we would also want to be talking about functions of random variables. So we remind you that we had this discussion that if you have a random variable x, and then you create a new random variable y by taking some function u of x, and if u is 1 to 1, then we had a way of working out what the PMF for y was. Okay? So we would like to know, what about if you have two random variables? Okay? If you have two random variables, if you have x1 and x2 are two discrete random variables, and then they get turned into new random variables y1 and y2. So y1 is a function u1 of x1 and x2, and y2 is a function u2 of x1 and x2. Then what is the new PMF, right? So we saw the something like this for one single random variable. Now we're transforming two random variables at the same time. Okay? If the transformation was 1 to 1, then we can talk about an inverse transformation. Right? So if y1 was equal to u1 of x1, x2, and y2 was equal to u2 of x1, x2, then let's say that the inverse transformation is given by functions w1 and w2. So x1 equals w1 of y1 and y2, and x2 is equal to w2 of y1 and y2. Then the joint PMF, right? Supposing you're assuming that you already have the joint PMF for x1 and x2. We're calling that f here. So the joint PMF for y1 and y2, what you do is you take the joint PMF for x1 and x2, and where you see x1, you replace it by w1 of y1 and y2, and where you would have seen x2 over here in the original PMF, you replace x2 by w2 of y1 and y2. Okay, so let's do an example. So let's say that there are two independent Poisson random variables. So x1 is Poisson with a rate lambda 1. x2 is a Poisson with a rate lambda 2. Let's invent two new random variables. Let's say that y1 equals x1 plus x2. And we'll say that y2 is equal to x2. So here, we're interested in knowing how the sum of two independent Poisson random variables behaves. Okay? And so let's find this joint PMF for y1 and y2. And then from this, we can recover the PMF just for y1 if we wanted to. Okay? Okay. So the PMF for x1 and x2, remember these were independent. So when you have independent random variables x1 and x2, their joint PMF is the product of the marginal PMFs. So this is just the product of the PMF for x1 and the PMF for x2. Okay, that's due to statistical independence of x1 and x2. Now, we were told that x1 was Poisson with rate lambda 1, and x2 was Poisson with rate lambda 2. So I take a Poisson random variable, I take the PMF for the Poisson random variable with rate lambda 1, and I multiply by the PMF for a Poisson random variable with rate lambda 2. So I multiply these two together, and using the rules for exponents, I can express it in this way. So now I have the joint, this is how I find the joint PMF. For the original random variables. Now, if I have this transformation, remember we said that now we can take the inverse transformation, and I work out that x1 is equal to y1 minus y2, and I work out that x2, well, we were given that x2 equals y2, right? Okay, so now I can take this, and I can replace x1 from using that transformation in terms of y1 and y2. And I can replace x2 in terms of y1 and y2. So this is what we do. The PMF for the new random variables y1 and y2, evaluated in y1 and y2, is given by the PMF for the old random variables, x1 and x2. I replace x1 in terms of y1 and y2, it's y1 minus y2. And I replace x2 here in terms of the new random variable. x2 is the same as y2. Okay? Now, well, this is the old PMF here. So I already had this was this constant, and then this was lambda 1 to the x1. I replace it by this. And this was lambda 2 to the x2. So x2, y2 replaces x2. Then I had x1 factorial down here. Well, x1 factorial is the same as y1 minus y2. And I had x2 factorial down here, and that I'm replacing that by y2. Okay, so that's how we find the joint PMF for the new random variables y1 and y2 from the old random variables. Okay, so that's an example for the joint PMFs and a transformation of two discrete random variables. Right, now if we have continuous random variables, then we talk about PDFs rather than PMFs. Okay, and again, I'm going to suppose that I have two continuous random variables, x1 and x2, and I'm getting new continuous random variables, y1 and y2. y1 is a function u1 of x1 and x2, and y2 is a function u2 of x1 and x2. Okay? If we suppose that these functions are one-to-one, then we can find inverses for them. So I can recover x1 from y1 and y2 by x1 is some function w1 of y1 and y2. And I can get x2 as a function w2 of y1 and y2. And now, how do I find? I have let's say I have the joint PDF for x1 and x2. I can find the joint PDF for the new random variables y1 and y2. So I take the old PDF. I replace x1 by w1 of y1 and y2. I replace w2 by, I replace x2 by y2 of y1 and y2. And now the difference from the old formula, previous formula, is that I have to multiply by the absolute value of the Jacobian. And here the Jacobian is a determinant, right? It's the partial of x1. Its entries are the partial of x1 with respect to y1, the partial of x1 with respect to y2, the partial of x2 with respect to y1, and the partial of x2 with respect to y2. So you calculate this determinant, that's the Jacobian, then you take the absolute value and you multiply that together. Okay, so let's suppose that, as an example, x and y are continuous independent random variables. They take only positive values, and we know their PDFs f sub x and f sub y. And we are interested in the product of x and y, so let's call that z. Okay, so we're going to let z equals x times y, and we can let w equal y. I'm interested in the PDF for z. First, I'm going to find the joint PDF for z and w first, and then I'm going to find the PDF for z. Okay? All right? So I was given that z is equal to x1 times y1. We're going to check, okay, so we're going to check if this transformation is 1 to 1. Well, if z equals x1, y1, and it's also equal to x2, y2, and w is equal to y1 is equal to y2, then we can convince ourselves that x1 equals x2 and y1 equals y2. So the transformation is 1 to 1. So then we can find inverses. Okay? So with a little algebra, the transformation in one direction was z equals xy and w equals y. In the other direction, it's y is equal to w and x is equal to z over w. Okay? We just should be careful that we're not dividing by 0. Well, we were given that y was positive and therefore w is always taking a positive value. Okay? Okay, so if we have x is equal to z over w and y is equal to w, then we can take the partial derivatives of x with respect to z and w. We can take the partial derivatives of y with respect to z and w. And we can put those into that determinant which we call the Jacobian. So if the partial of x with respect to z is 1 over w. The partial of x with respect to w is minus z over w squared. The partial of y with respect to z is 0. And the partial of y with respect to w is equal to 1. Okay. Then we would need to calculate the Jacobian. We put these partial derivatives into the determinant, and we evaluate that determinant, and we find that the determinant is equal to 1 over w. So the Jacobian is 1 over w. We need the absolute value of the determinant, but we were told that w was bigger than 0. So we can just keep that as 1 over w. Now, so what's the joint PDF? The joint PDF is given by the PDF, the joint for z and w is given by the joint for x and y, but you're going to replace x in terms of z and w, you're going to replace y in terms of z and w times the absolute value of the Jacobian. Okay, so now we were told that these were independent, x and y were independent. So when x and y are statistically independent, the joint PDF is just the product of the marginal PDFs. So we replace the joint PDF by the marginal PDFs. Right. Now, when this is in terms of the old x and y are still there in terms of the old variables. I replace x in terms of z and w and y in terms of z and w, right? We had that x was equal to z over w. So I replace x by z over w. And we had that y was equal to w. So I replace y by w. Now I have this PDF for z, joint PDF for z and w completely in terms of z and w. We were interested in the marginal PDF for z. How would we get that? Well, we would integrate the joint for z, is the joint for z and w. We would integrate with respect to w. We'd integrate the w out, and that would leave us with the marginal. That would leave us with the marginal for z. We were told that w can't take negative values, so we're going to integrate from 0 to infinity. And since we aren't given any more information about this, we don't, this is as far as we can take this.